Our next topic is to deal with some of the dangers of concurrency. We saw in the in the snow scene example that sometimes we got these error messages when we were modifying the lists of clouds and snowflakes, things like concurrent access, uh, uh, other messages similar to that. And what we want to do is take a look at really what's going on there. And it all comes down to this idea of interference. And we've been talking about how when we have objects that extend thread, and you call the start method, which in turn calls their run method, those run methods for all of the threads that are in your program are happening at the same time. Now think about this in other contexts, like in the notes here, it says, imagine if your body had two brains, and one of the brains gives instructions to do one thing, and the other brain gives instructions to do something else. If your muscles are receiving these different messages, it's probably not going to be good. Some muscles might be doing the things that one brain says, and others might be doing what the other says, and we'd have a big problem. Same idea here in threaded programs. We need to make sure that the brains in our program, all the threads in our program, either only give one message at a time or give consistent messages to different parts of our program. And we'll see how that plays out here. So what we're going to take a look at to demonstrate this is a series of examples, all of which come through this GitHub repository here, ATMConcurrency. If you haven't already done so, please grab yourself a clone of that and bring it up in your favorite Java environment so you can follow along. Really what it comes down to in all these cases is that at some level you have individual variables. Sometimes it's parts of data structures, but you have an individual variable that's being told to be changed in two different ways at the same time. So I'm going to go over to my copy of this ATMConcurrency. Let's move over here. ATMConcurrency has in it three subdirectories, Danger1, Danger2, and Safe. We are going to start in Danger1. In each of these, we have three Java files. There's a class that represents a bank, a class that represents an individual's account at the bank, and an ATM class which processes transactions on that account at the bank. We'll start out by taking a look at the bank class. I've got it loaded up here. The bank class is what brings in the graphical user interface. So we have as we have in many of these cases, we have a run method that sets up a window layout. Some of this is a little different than things we've seen, but it's pretty similar. Basic idea is we have a bunch of labels, and we put them in some panels, so it looks pretty reasonable on the screen. There's a little bit of messing with fonts. And then we have a button at the bottom, which is to run our demo. And we have an action listener on that button that calls this action perform method right here. So before we go any further, let's run it, compile it up and run it. So when our bank starts, we have an initial balance of 1,000, a current balance of 1,000, and so far we've withdrawn 0 and we've deposited 0. And before we actually run it, you can take a little look over here at the code. What's going to happen when I press that run demo button, it's going to create two of these ATM objects. Well, it's first going to create an account object, and then it's going to create two of these ATM objects. And we're going to start each one. So press the start button essentially on each one, make it go live its ATM life. An ATM is also a thread. And in this thread, well, when we construct it, we just remember which account we're operating on, how much do we change. A positive value is a deposit, a negative value is a withdrawal, and what label do we need to update back in the other window with our current balance after we've modified it. And so this guy's run method is, again, fairly similar to a lot of the run methods we've been dealing with. It runs this loop a certain number of times, however many transactions we're supposed to do. And we can take a look at the top. The number of transactions is 10. and we're going to wait 400 in between transactions. So back down in here, this loop is going to go around 10 times. Each of those 10 times, we're going to ask our account, what is your balance? And then we're going to set the balance to our old balance plus the amount we're supposed to add. This will decrease it if change is negative. We increment our total for the total amount that we've withdrawn or deposited, and then we wait for as long as the next transaction is supposed to happen. We also have this small random amount of sleep here, and as the comment says, this is here to force some problems. But even without this, we would be likely to see some problems in this situation. Take a quick look before we run it at the account class. You see the account class here needs to have a get balance and a set balance. It also has a constructor. It just remembers a little bit of information that it's responsible for. How much is its start balance, and where do I display my current balance at any given time when it changes. Get balance just returns the instance variable balance. Set balance makes the balance equal to whatever we have as this parameter. This would be a wonderful thing in real banks if we could just tell them, here, this is my new balance, without any kind of check on it. But that's all right. So anyway, back in my program, when I click the Run Demo, well, first, let's look back at bank for a second. The two ATMs we're going to create, one of them is going to try to deposit 100 10 times, and the other one is going to try to withdraw 100 10 times. So in the end, after these things each make their 10 transactions, we should have the same amount of money that we started with. So if I run it, we can see that we do all 10 of our transactions, and for some reason, we ended up with $200 less than we started with. So that's not very good. We're not very happy about that. If I try it again, it resets it back to the beginning. This time, it looks like there's an error, but this time the error is in my favor. So this is great. I like this bank. I withdrew 1,000, deposited 1,000, and ended up with 600 more than I started with. And if I keep doing this, sometimes I might get the right answer. Oh, conveniently I did that time. And sometimes I'll end up with an error in the bank's favor. And sometimes I'll end up with an error in my favor. This one looks like it's going to the bank's favor again. And we could try this over and over, and we keep getting different answers. They tend to be not too far off from right, but if you're running a bank, you'd like to make sure that everything happens properly. And the problem here, as you might have guessed, and it's described in the notes here. So try to take a look at the code and see where you see a problem before you look at the notes or listen to the rest of this video. So if we look at the ATM here in Danger1, we have two ATM objects, both one's trying to repeatedly deposit 100, one's trying repeatedly to withdraw 100, and let's say they both get to this point about the same time. They both get here and they both ask what's the balance, and they both get 1,000. They each take a little bit different amount of time to do their work. There's all kinds of reasons that could happen in real life. This one, we're forcing that issue. And then they both set the balance to their new amount. So if they both got to here and got a 1,000, one of them waited 2 milliseconds and set the balance to 1,100. The other one waited 4 milliseconds, and then it would set the balance to 900. So I did one transaction of a deposit, one of a withdrawal, and somehow the deposit one was it never took effect. Well, very temporarily took effect, but its effect was erased by the withdrawal ATM that had checked the balance too soon. So basically the problem is there's this delay in between checking the balance to do the math and set the new balance. And depending how these two ATM objects interleave their actions, we would get more and more potential for errors in this case. So anyway, These interleavings of operations are the key thing that we need to be thinking about. What we see here is an example of interference, and more specifically, it's called a race condition. The two threads race each other to figure out what's the new balance, and then they set it. Whoever is the slowest wins. Whoever took the longest to decide, their transaction is the one that takes effect. So this is definitely a problem. There are ways that we can fix it, or we can almost fix it. We could remove this sleep in here. We could say, well, what are the chances that we're actually going to have a problem if I don't sleep? It's more likely that we're going to get the right answer in this case, but it's not guaranteed. And if you're running a bank, or you're the customer of a bank, even without that code in there, we did see an error this time in our favor. So as either a customer of the bank or the bank, you want to make sure that this kind of thing doesn't happen. And we'll take a look at some ways that we can deal with that starting in the next video.